Alrighty, thank you everyone. Welcome back to Main Hall. We are here for Iwan Vosloo, who's going to be talking about packaging for your database schema and schema migration. Iwan coaches agile teams in the corporate world. This includes helping programmers to apply practices such as testing and object-oriented design in the context of existing systems that have grown convoluted and debilitating over time. I must say, I'm very grateful. I've never worked on systems that have got complicated over 15 years of craft. Oh, no, never. He makes the application, or rather, that kind of thing makes the application of such practices challenging. Now, the craft builds up, there's ancient systems running. We know the story. His spare time goes into REAL, which is REAHL, with a silent H, a collection of projects related to Python-based development. Iwan? Let's go. Thank you.
Thank you. Good morning, everyone. And just a thank you to the organizers for pulling this off again. I've spoken here before about the stuff that we do. And before, it used to be very much focused on web stuff. This time, it's something different. We had to do this, and we're a little bit stoked that we managed to get it right. So I wanted to share. Just in case there's someone who don't know what database migration is about, here's a sort of a blitz introduction. So we write code that's dependent on what's in a database. In our case, in particular, we use SQL Alchemy, ORM, which maps a class like what you see there on the screen to a database table to store instances of that class. And for SQL Alchemy to be able to do that, it creates a database schema that obviously matches what your code expects. So what typically happens is you start off with a schema like what we have here on the left, and run with that system for, I don't know, some time, and it accumulates data. And then, of course, in that time, you change your code. And it might be that your new code actually needs a different schema. So database schema migration is all about how do you make little changes to the existing schema to make it match the new one and not lose the data in the process. So there are tools around to help you with this. In our particular case, SQL Alchemy has a tool called Alembic. And Alembic can generate Python code that does this for you each time you make changes to your code. It gives each of these so-called migrations a version number that looks a little bit like Git, and if it does look a little bit like Git, I think that's their intention, because they know to run these things in a particular order to get to the final state of your database, and they also keep track in the database of which was the last version run, and help you with some stuff like branching and merging these things. So it's very much focused on sort of the development life cycle. Django does something a little bit smarter, because Django has got this plugin system, if I may call it that, in the guise of Django's apps, where each app can have its own migrations. And what's of particular interest to me is the fact that the migration of one app can actually be dependent on the migration of another app to run. Now, I'm not a Django expert, so those of you, please come pull me aside afterwards and tell me. I don't know how smart Django can be about the order in which things are run. And throughout this talk, you'll see exactly what I mean when I say that. From what I could see, a programmer has to specify quite a bit of that. But please come and enlighten me. We wanted to do something entirely different, actually, because we were looking at the Python packaging world and realizing that those packages in PyPI already all have versions. And presumably you would want a particular database version that works with each version of your package. So we know this world sort of more from the point of view of code, where you say, ask pip to install some package, and it will run off, get the right version, figure out all the right dependencies, and download them all for you and install them. What is in a package typically, and I'm just gonna talk about the real main things here. Typically, a package these days is a wheel, which is a compressed archive, which contains a bunch of metadata about your package. Most importantly, maybe for this talk, is the fact that it knows which other packages it's dependent upon and at which version. And then, of course, it's got all your source code in it. So what we really actually wanted to do is to add to this your migrations as well. What makes this a little bit challenging is that you must remember that all the packages out there in PyPI are authored by different people. They don't really want to, and it wouldn't be fair to let them know about the intricacies of all the other packages that play along. And also, you don't know when you install a particular package or when you author a particular package, you don't know with which other packages it will be installed together in the same database if you do this kind of thing. So we wanted to automate maybe a different set of things. Before we launch into it, a couple of things. What is a dependency on a database level? Because we know that packages are dependent on one another when we import code, typically. But it might be that I have a package like this one here that I've shown you before, and someone else comes along, creates a different package, and in that package they actually write code that results in a foreign key to my package. So this is sort of the basic database dependency that we sit with. Knowing that, you also need to understand what can change over time with these things. Here's a simple example. In this example, the package on the left is going to change, and it's going to split that table into two. And once it does that, all of a sudden, all the foreign keys that used to point to that particular column now needs to point to a different column in a different table. And there's some intricacies regarding this, because if you sit with this state in your database currently, you have to do things in a particular order to get to the end result. So first of all, you need to drop all the foreign keys, constraints, before you're able to tear that table apart and make a new one. And then finally, you can create the constraints pointing to a different table. And if you get the order wrong, then you've got problems. I want to simplify this a little bit. This example will be very difficult to put on slides and talk you through. So I'm going to pretend that you need the same order requirement when you just rename that column that foreign keys point to. So let's pretend this is what you have to do. So it's not strictly speaking true, at least not for PostgreSQL. I don't know about other databases. But I have a lot of examples to go through, so I want to keep it simple. And also, I use a little bit of a shorthand here. If I write PK something, it means there's a migration that says create a primary key column called that. If I say FK something, it means create a foreign key constraint to that column. If I say PK something to something else, it basically means do all the various things you need to do. And in this example, I said drop the primary key, rename the column, recreate the primary key constraint. If I say FK something to something else, I similarly mean you need to drop the foreign key and recreate it differently. So with that in hand, I want to run you through an example of what can happen in the real world. Let's say somebody comes along, they write a package, C, at version 3.0, they release that, and in it contains a migration that says create a primary key and create a foreign key to it, and it's called key C in this case. So somebody else could come along and say, okay, I want to use your stuff. I'm going to release package B, version 2, and it's got a foreign key to that key C. And let's say there's another package, the details I don't want to go into, and let's say I come along with my package. I depend on all of these things, and I also have a foreign key to that key C. And then there's another iteration of these things. All these people bring out new versions. And in this case, C3.1, the authors there have decided that they want to rename this column from key C to key C1. So that's straightforward. They have to do all of those things. But B, coming from B0, it knew that it was dependent on key C. So in its case, it needs to rename it from key C to C1. So this is fairly straightforward, I hope, still. But now the authors of C are very prolific, and they come out with yet another version of C, in which they rename this thing once more. This time from C1 to C2, because you see there the previous version of C had it called C1, but now we're just going to C2. And nobody really bothered to use that version. So they came out with yet another version in which they renamed it again to C3. And then everybody else started to join the club. And an interesting thing happens here, because the authors of B now know that previously they called it C1. So they actually just want to write the migration that says remove C1 and put a constraint on C3, right? They're not interested in knowing the intermediate steps. And similarly, with my project, I can come along and jump even more renamings and just care about renaming from C to C3. There are two little tricks hidden in this graph. Well, one maybe I've spoken about already. And the one is this dependency between A and B. You will notice that in the first iteration here, A was dependent on B, but dependencies can also change over time. So in the second one, at the bottom there, B is now dependent on A. And that can shake things up a little bit. Also, when something like this happens, when there's an intermediary version and no one actually uses it, it can create a tricky order for things to happen in. The other thing is, you'll notice that there are sort of clusters of projects that are designed to work together with one another. So they can exist in the same database together, and it would make sense. So armed with all of this, let's see if we can try a naive migration attempt. So let's assume that everything on this left cluster under my project 1 is up to date and the database is created, and we just want to upgrade to my project 2. So one thing that we could maybe try and do is to jump to the next cluster, which is the one at the bottom in the middle there, and maybe start with the highest version in it, which is that B 3.0, and let's drop all the foreign keys. So you can drop key C because it exists on the left, and that's fine. And let's move down to C 3.1 now and do its migrations and drop its key C, and it can do that. But now you have a problem, because you can't drop the primary key called C because there's still a foreign key pointing to it, right? Let's try another one. We can try to start from the top and say, okay, let's start from my project. Let's drop key C according to this guy, or this guy's foreign key. But then with the very next one, we've got a problem, because key C1 doesn't exist yet. And this is what B 3.1 actually thinks should be there, based on what its previous versions are supposed to have. So there are, of course, many different configurations of these graphs and so on. But the good news is that there is actually a traversal that works. So once again, assuming that everything has been done on the left cluster here, and I want to use that space to just keep track of what's happening in the database so that you can follow along. What we've come up with is that you start with a highest cluster in dependency order, basically. And in it, start with the highest version as well, and ask the question, does its previous version point to a cluster that we haven't migrated yet? In this case, we've done it already. So the answer is no, and that means we can actually drop its foreign key, in this case, the key C. And now we can move down in these versions and go to B 3.1 and say, okay, does it point to a cluster that we haven't done before? It does. So that means we sort of suspend what we've been doing there, jump to that cluster and start with it at the highest level here. And again, ask the question, does that B point back to something we haven't dealt with before? We've dealt with it, so we can actually drop its foreign key and the key C disappears. We move down to C. We can ask the same question, the answer is the same. So we can say, okay, drop its foreign key. And now we've basically done everything in this bottom cluster, so we can start moving up. And part of moving up is we can start also dropping the primary keys. And as we move up, we can start recreating the primary key and the foreign key for C and as well for B. And then we're done with this cluster, we jump back up. But we're not done with the guy on the top. We basically just popped back. So we're still busy on our way down there with dropping foreign keys. So we will actually, sorry, I missed that. I don't know if you saw that. Since we've now finished with the cluster that this B actually led us to, we can actually drop the foreign keys in it. Okay. Then we can move on to the rest of the things. We'll get to C. Again, we ask the question, does it point to another cluster that hasn't been handled? It does. So we have to basically jump to that one. And in here, we can now safely do, okay, C also points back to a cluster that we now have done, which means we can now delete C1 because it now exists. Previously, it wouldn't have existed, but at this time it does. And similarly, we can drop the foreign key called the primary key called C1, and we can recreate these things. Then we're done with that little cluster, we jump back. And since we're now on our way back, we can drop the foreign key as C is indicating there, C2, because it now exists. And similarly, the primary key, we can recreate all of them. And on our way back, we can recreate the foreign keys of each of these other projects, and we're done. So there is an order in which this happens. Implementing it can be tricky, so I want to just show you a couple of high-level things about that. So first of all, what Alembic gives you is basically a library that allows you to call methods that change the database schema in one way or another, like these. And you typically would want to write things like drop this constraint, create the foreign key, alter column, and so on. Now, in our example, this order of doing things is actually not going to work, right? Because you can't create the foreign key to key C1 before you haven't renamed that thing to key C1. So instead of actually doing this, what we've come up with is this idea of migration phases. So we basically say that first, we typically want to drop all the foreign keys that are relevant. So instead of actually doing the drop constraint, we'll sort of keep track of the fact that we need to do it in the drop foreign key phase, and so on with all the other things. So it doesn't really matter then in what order you put them, because they will actually be ordered by the migration engine when it runs. Just to show you what it looks like in code, so instead of actually calling these things, we call a method called schedule to say, okay, well, schedule the drop constraint operation in the drop foreign key phase and give it all the arguments. And it's just a method that's going to be called with those arguments at the appropriate time. Right, so you've seen the migration clusters that we had in the previous slides. This is just a zoomed out view of them on the right. So we draw that graph as well. And based on that graph, we create yet another graph, which we call migration schedules. Those are the things on the left. So basically for each cluster, remember I said all the versions in that cluster are basically made to work together. So all of them, we create a migration schedule, and a migration schedule has all these phases in it. So all those phases happen for each cluster. Depending on what this graph on the right looks like also, the graph on the left could be different. In this case, my project 2.0, we basically name these things after the top level version in them. So my project 2.0 will have 3, so we call them nested migrations, because you have to sort of do all the children there before you come up and do the parent one. But various different configurations of these graphs result in different graphs along the way as well. I just want to zoom into one of them. If you look at my project 2.0 here, the drop foreign key phase internally is actually a bunch of phases. Because if you remember correctly, we didn't have an example of this, but there are some foreign keys that need to be dropped before you actually go and do the migrations of your nested schedule. And there are some that need to be done after. And similarly, with each other nested one, there is some that needs to be done before it and after it, and so on. And once you've done all the foreign keys and all the nested migrations, then you can actually do the other things like alter tables and create foreign keys and so on. You've seen this before. This is a slightly different one, but I just wanted to sort of point to it a little bit, because in this particular migration, which I am now writing, let's say, in my package, because I know what changed from my previous version to now, I'm going to say I'm going to have to drop the foreign key and recreate it pointing to something else. And I want to do those two things together. First of all, it's code that belongs in this package, and no other package will have it. But the interesting thing is that these things are going to be executed at wildly different times, according to the algorithm that I just ran through. To use all of this, of course, you don't need to know the implementation details. I'm just very glad we managed to find a way to traverse those graphs. But so to use it, you need to add some stuff to your PyProject file. First of all, the build system is going to require that real component metadata project of ours. It is basically an extension of setup tools. This is not all. You actually need to specify a bunch of real component specific information for us. So for each version that you have released, you basically need to specify which were the other projects and which versions that it used to depend on, even though it's a historical version, because that allows us to build all these graphs. And also, of course, you need to know which migrations you are shipping for that particular version. So there's actually more stuff to this real component project. We actually made it a separate project so that it can be used completely on its own. We also package a bunch of other things like translations for different languages. We can also package a migration for one package in a different package, a language, sorry. We've got a way of configuring things per package also, and so on and so forth. So I see we still have a little bit of time, so I've got a couple of bonus slides I'll go into. But just to put this into context, if you go into our website, you'll find this under real component, because we broke the thing into a bunch of little smaller projects. I'm going to skip that slide and just show you this. So if we run migrations, you get output something like this, or if you ask it to be verbose, and you'll see there on the left-hand side, those are the classes that the migrations actually were written in. If it says in something, that's actually part of the migration cluster in which it ran. And then, of course, the actual thing that runs comes thereafter. What we also have is, if you have GraphViz installed, you can ask it to do some planning, and then it will generate a graph like this. In this particular case, this graph is all about figuring out what those clusters are, and it's a bit more complicated in the real world compared to the examples that I showed you, because You won't necessarily see them as distinct components in this graph, but they're definitely all the roots of different dependency trees in this graph. This was a difficult one to fit onto a slide, so these are the clusters that are created from that. And once again, because there are all the real things also part of this, the graphs are a bit bigger than what I showed you up to now. And similarly, there are the schedules. And with that, I'll end. If you want to install this thing, I just included it up there, what all you need to install to run this. The example that I used for this talk is on GitHub, if you want to play around with it. And if you want a link to the talk, use the bottom one there on our site. Any questions?
Well, thank you, Iwan. I'll point out this kind of database migration stuff can be stupidly tedious. You know, make one tiny change to your database and nothing works. You know, what was your foreign constraint? You know, well, I don't care. You know, it's a new row, but this makes it look a heck of a lot easier. So, awesome. Thank you, Iwan. Do we have any questions? I see Andrew. Sir? Full of questions. I like that.
So I must be honest, I really tried to follow, and I wasn't sure how you knew when to traverse down versus across in when you were going through a few slides back. That one.
Okay, let me try and get to the beginning here.
Okay, and then together with that, is there a scenario where this will break, some kind of cyclic dependency or some kind of things that break this?
Cyclic dependencies are something that we detect before we start. So we break and complain about that because they don't really make sense anyway for dependencies. So yes, that will definitely not work. As to your question about the order here, so we start at the sort of topmost cluster in dependency order. We infer the dependencies. You need to specify for each package what else do you depend on, but we can infer which is the previous version of your own project. Okay, so there are two kinds of dependencies here. The one kind of dependency is, oh, I'm dependent on that project because I use it. The other kind of dependency is, I'm dependent on the previous version of my own project because that's where I need to migrate from. So as to the order that you asked about, so I'll go through just the beginning of it again. So we look at this, the top, again, in dependency order within the cluster, the top version there, and say, is its previous version in a cluster that we haven't migrated yet? And if, like in this first case, we have now migrated the first one, so that means we can actually, I'm not far enough back. There we're starting. So then we can delete or do the first one that removes the foreign key, drops the foreign key constraint. But later on, like in this case, it does have a version that is in another cluster which we haven't done yet. And in that case, we have to sort of suspend everything and jump down. Thanks.
Microphone works better when it's on. Is that covered, Andrew? Good. Further questions? Anybody got any further questions? Going once? Going twice? Cool. Thank you, Iwan. It's one final check because I have occasionally missed questions in here. I don't think I see any. Just a moment. This is not that easy to drive. My thumbs are too big, basically. Let me bring you the mic so it's on the recording.
Okay. The execution plan, I presume that means taking those steps and making sure that they are flattened in the right order and applied at the right package. Is that why you say the migration can occur at different parts of a migration can occur at different times as you're going through the execution plan?
As depending on the layout of the graph, which will depend on which other projects you use and who's dependent on whom when, the plan can be different. But the plan basically means, if I can go back here a little bit, the plan basically means, first of all, creating this graph. Sorry, it's a bit far back now. Creating this graph just of the versions themselves, and then creating both of these graphs. And while we create these graphs, we actually call the migration code that says schedule, schedule, schedule. But because it's just scheduled, it doesn't run yet. So it basically collects everything it needs to do, and it knows the right order because of what all the graphs look like. And then if you say do it, it just runs through them and do it.
Thank you, Ivan. I think that's all the questions. Nobody has any questions online. So, Ivan, thank you very much. That was very good. Awesome.
Thank you.
Thank you very much.